Hey everybody, in this next video lesson we're going to talk about the process of writing chemical reactions. We're going to look at going from words to symbols and also from symbols to words. Now this might sound familiar to you because we did writing words to symbols for ionic compounds and molecular substances back in the first trimester. But now we're going to put it together and we are going to be writing out full chemical reactions, not just molecules and compounds, but whole reactions. So you're going to need to draw on that knowledge that you gained from last trimester when it comes to translating from words to symbols and symbols to words in entire chemical reactions. But before we begin with that, we need to talk about a couple of things that are important when writing chemical reactions. And the first thing are diatomic molecules. Now, depending on your chemistry teacher from first trimester, you may already know what diatomic molecules are. But let's review them because it's new to some students, especially students who had me as teacher in first trimester, because I did not talk about diatomic molecules. What are diatomic molecules? Well, these are substances when found pure in nature always come in pairs, and they are nonmetals. Not all nonmetals, but these specific nonmetals. They are H2, N2, O2, F2, Cl2, Br2, I2. These are the diatomic molecules. So if I say just hydrogen, it's assumed to be H2. Or if I say fluorine, it's assumed to be F2. There are no individual fluorine atoms just floating out there in nature. They always come in pairs. Now they may be bonded to something else, like, for example, if sodium is bonded to fluorine, well then it's NaF, because the charges of balance. I'm not saying every time you see fluorine put a 2 behind it. What I'm saying is every time you see one of these elements written in a chemical reaction, they're not individual elements, they are paired up with one of their own. So when found pure, and that's key, pure in nature, they come as pairs. If they're not pure, well then it depends on what they're bonded to determine their amount. So it might be a good idea on your periodic tables that you have, and you can write things on, to maybe put a little star in the corner of each one of these elements so that when you see them, you know that they are diatomic molecules. But also to help remind you, if you flip over your periodic table to the back, where you'll find all the polyatomic ions, in the lower left-hand corner, you'll also find a list of the diatomics. And you'll also notice that on that list, At is also considered diatomic, although that substance is radioactive and is not very common. I, in fact, have never used At as a diatomic molecule in an example, but it is listed there. So all the diatomics are listed for you on the back of the periodic table. Now let's talk about states of matter next. States of matter, as you know, are solid, liquid, and gas, and these are the three common states of matter. And when you're writing out chemical formulas and chemical reactions, you need to include the states of matter if we list it. So for example, if we say solid sodium fluoride, well then you'll have a little S behind it for solid. Or if I say liquid water, you would say H2O with an L for liquid. Or if I say maybe hydrogen gas, you'd say H2 with a G for gas. Now there's a fourth state of matter, which isn't really a state of matter, but it's more of a condition of matter, like how is it presenting itself in the real world. And usually solid substances don't react very well, ionically anyway. They don't react very quickly. In order to make them speed up their reaction, what we do is we take an ionic substance and we dissolve it into water. And so if we dissolve it into water, we say it's aqueous. The prefix aqua or aqua means water. And so an aqueous solution means it's ionic, but it's been dissolved into water. So for example, you can take sodium fluoride solid and dissolve it into water, and what you have is aqueous sodium fluoride. Now let's talk about how we are going to translate these chemical reactions from words to symbols and from symbols to words. We call these skeleton reactions. Skeleton reactions only have the chemical formulas for the reactants and products, but they are not balanced. So you may see unequal numbers of sodiums or unequal numbers of nitrates or unequal numbers of other ions on either side of the reaction arrow because they are not balanced. In fact, we're going to do balancing in a future unit. So these are just skeleton reactions. We need to basically just make sure the formulas are correct. Now let's first start talking about translating from words to symbols. Now, of course, these chemical reactions are going to have ionic substances. They're going to have covalently bonded substances. And you need to remember all of your rules that you learned about in first trimester for translating from words to symbols. For ionic, for example, it's all about balancing charges. It's all about making your pluses and your minuses cancel each other out. So when I say calcium carbonate, you can take calcium and carbonate, identify their charges, and translate that to the proper symbols. Or if I use covalently bonded substances with prefixes like sulfur trioxide, well, you know that it's sulfur and 3 oxygens. So it's all about translating from words to symbols. With ionic, it's balancing charges, and for covalent, it's just making sure that your prefixes turn into the right formulas. Obviously, don't forget about the states of matter as well. So if I say solid or liquid or gas or aqueous, we need to include that in our translation. What about translating from symbols to words? Well, this is the opposite, right, of from words to symbols. So if I give you a chemical reaction in symbol form, you need to basically write out a sentence that takes the chemical symbols and converts it to words. So for ionic substances, these might end in IDE or ATE. We need to remember our polyatomic ions. For transition metals, they may include Roman numerals. And for covalent substances, we need to include the prefixes. So you need to identify, is this an ionic substance? Is this a covalent substance? This is why this is so important in a previous trimester. And this is why it takes lots of practice, because this stuff doesn't go away. Let's take a look at a few examples. So for these first examples, we're going to translate the following from words to symbols. In blue, I have the sentence form in the chemical reaction. So let's begin. Hydrogen gas. Now, hydrogen is one of my diatomic molecules, so that needs to be H2. And I'm going to put G for gas after it. And is a plus symbol. Iodine gas. Iodine, also one of my diatomics. So I'm going to put I, and then a little 2 behind it, and gas, combined to form. Now, this is my verb. This is my reaction arrow. So I'm going to react to form. And then gaseous is another way of saying it's in its gas state. Hydrogen iodide. So I'm looking at this, I'm translating, I go hydrogen. Oh, that's a nonmetal, and iodine's a nonmetal. But wait, when hydrogen's first, it's acting as a cation. So it's hydrogen +1, iodine -1. So I'm going to balance the charges, HI, and just make sure I put a little G behind it for gas. And that's how you translate from words to symbols. Here's another one, a little bit more complex. First, lithium solid, or solid lithium. So that's Li. It's not charged, it's just pure lithium. And it's not a diatomic. So I don't need to put a 2 behind it. Remember, your diatomics are only hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, iodine, and astatine. So lithium can be by itself. And is plus. And then aqueous, zinc 2 nitrate. Ooh, I got a Roman numeral here. The Roman numeral is telling me the charge of the zinc. So it's a +2 charge. And nitrate, that's off the back of the periodic table. It's NO3 with a 1- charge, or -1, depending on the teacher you had from first trimester. 1- -1, really doesn't matter. I need to balance the charges. So it's Zn NO3 parentheses 2. Reactive form, so there's my reaction arrow. Solid zinc, not diatomic, and aqueous lithium nitrate. Remember, I need to, once again, balance the charges. Lithium is a +1 charge, nitrate, -1 charge. So I just smush those together, LiNO3, and put an AQ for aqueous. The last thing we're going to do is translate from symbols to words. So I've got a chemical reaction in symbol form, and I need to translate it to words. Make sure I include the states of matter. So this first one is KBr. This is potassium bromide. Because it's just a bromine, it drops the ending and adds IDE. So potassium bromide, and I can put aqueous as the first word or just after it, doesn't really matter. So I can say aqueous potassium bromide and Ag and ClO3. This is silver, and this is chlorate, so silver chlorate. Now, because silver's a transition metal, I need to remember the Roman numeral. So remember that also polyatomic ions, even though we don't write them with parentheses around them, if there's a 1 down here, that means that there's one of these ions, and I need to figure out the charge of the silver that combined with the chlorate. Well, chlorate is a -1 charge ion, and there's one of them, so that must mean that this silver is a +1 charge ion. So now I know that it's silver 1 chlorate as the name, and that is also aqueous. Reacts to form potassium chlorate, aqueous, and silver 1. If it was a 1 over here, it's a 1 over here also. Silver 1 bromide, solid. And that's my sentence. Next, I'm going to do this bottom one, and I've included some covalently bonded molecules in this one. And I want to give you a little bit of everything. I wanted to give you some Roman numerals. I wanted to give you some covalent. So I want to give you some polyatomic ions as well. Let's check this one out. Calcium carbonate solid reacts to form calcium oxide solid and carbon dioxide gas. When I see nonmetal bonded to nonmetal, then it's a covalent substance and I need prefixes. Where if it's a metal bonded to a nonmetal, that's ionic. So I don't use prefixes in that case. Now, chances are this is going to take a bit of practice for you to really master this. But luckily for you, we have lots of practice problems in a worksheet that we can try. Well, that takes care of this video lesson on writing chemical reactions. Thanks for watching.